Okay, our 10th presentation this afternoon is from Sabri Kais, and the topic is quantum machine learning for data analytics and optimization. Floor is yours.
Thank you. Okay, good afternoon, and thank you for the invitation. I'm going to talk about is combining quantum computing with machine learning, and this is what we call quantum machine learning for data analysis, analytics, and optimization. And with me, my colleagues, Alex Botham from computer science, Young Chen from physics, and Ashraf Alam from electrical and computer engineering. We have our own extensive network, and this proposal is also open for faculty as we go on. So what is the big idea? In analogy with the Big Bang theory in physics, here we have explosion of data. And it is the IBM just released a report that every day we add at least one petabyte of information. And this is 10 to the 15 byte of information every day we add it to our database. So we have a huge database. And the question is, how do you analyze this huge database? How do you get information out of this one? And so our idea is to develop the game-changing quantum algorithms to perform machine learning tasks on this large-scale scientific database. And the second point, this is the time to launch an externally funded major center for quantum machine learning for data analytics and optimization. And specifically, we will go to work on 3 big projects. The first one will be chemistry and material design, mainly focusing on quantum materials, and this will be led by myself and Chen from physics. The second project will be about solar optimization and the solar farm lifetime as a function of weather parameters. And this will be led by Professor Ashraf Alam from electrical computer engineering. And the third project will be about grid stability. And this will be led by Alex, who is here. And just to give you an example, the data collected from 1,000 units for the grid stability, it's of the order of 3 petabytes every day. So we have a huge database. And the question is, how do you manipulate, get some important information out of this huge database? So what is the approach? The approach, as I mentioned, we have 2 frontiers of methods, quantum computing and machine learning. Machine learning touches every aspect of our life. The same with quantum computing, near-term application. And the question, how do you put those 2 together in order to do quantum machine learning? And just quickly, the quantum machine learning, if you compare with the traditional programming, you have data and program, and you feed it in the computer, you get an output. And the machine learning, you go to learn from your output to fit a program, and the idea is to go back to the classical machine and probably predict outcome. For the quantum machine learning, we'll perform everything in the quantum computer, and we use quantum data. And the idea of using quantum data, you have exponential speed up. And this is the promise of quantum computer. So just to give you an example, if you have terabyte of information, like 10 to the 12 bits, once you perform this in a quantum computer, we take the exponential, you have the log, which is 40 qubits. So with 40 qubits, you will be able to manipulate 10 to the 12 bits of information. So these are logical qubits. You can ask, what do we have today? Today we have, with the D-Wave, we have 2,000 qubits, but this is a special machine for optimization. IBM released 55 qubits and Google 72. But these are physical qubits, not logical qubit because of the error corrections. Just to give you an idea how difficult it is to do quantum design materials. So if I look at the accuracy of designing materials as a function of cost, when we say designing material in quantum chemistry, we solve the Schrödinger equation, which is here. So over the years, I mean, this is not a new field. We're developing methods for the last 80 years, and you can see we have 4 Nobel Prize winners along the development of this theory. But just here, I gave example, if you would like to do calculation for the aspirin. Aspirin is 21 atoms with 90 electrons. And if you'd like to do accurate calculation at the 1 kilocalorie per mole, you need the scale of years with CP units. So there is no room to design materials accurately enough with what we have today. So this is why we said maybe with the quantum machine learning, we have the promise to scale up with the quantum speed up. We can do high accurate calculation at the lowest computational cost. Now, with this approach, we put an interdisciplinary team together to tackle these big problems. Myself comes from quantum chemistry and quantum computing. Alex is an expert in matrix and graph algorithms, and he is involved in the DOE exascale supercomputing project. Professor Allam is an expert in solar farming, solar cell derogation model, and large process simulation, who has previously developed a classical machine learning algorithm. And Professor Chen, the director of the Quantum Center here at Purdue, is an expert in quantum materials and will help us in designing new quantum materials. So the benefits. I mean, just by reducing the scale of the database from these petabytes to something manageable will benefit the energy, the public health, the security, the business. And here, with the 3 projects, we'll be able to monitor the stability of the grid, designing a new material for photovoltaic applications, management program for solar farming installation. And in security, just last week with my students, we were able to also look at how machine learning can help us in factoring numbers, which is important in the RSA security. And of course, in the future, maybe with teaming with industry, we can look at other problems like transportation, traffic management, which is all about optimization. Now, who are the competition for us? Mainly, I see Google Lab, IBM, and Microsoft, where they developed what we call the Quantum Artificial Intelligence Unit. And I know the 3 directors of this program, and we worked with them before. We have collaboration. So I think it will be easy in the future to talk with them to support our program in quantum machine learning. And why Purdue? We have a leading faculty here in their field. We have excellent infrastructure in the Discovery Park, different centers, and we have supporting leadership. Now, what about the budget? The budget, we are thinking about $300K for 2 years. For students, we'll have 154 students. We're going to support 3 joint students between the 4 of us. Faculty, 100K to buy time and mainly to focus when there is a chance to write a proposal or we need their efforts. And for workshop and travel, it's about 50K for 2 years. And the idea to meet the funding agency and go to travel to talk about our research. And now the time achievement for the first year, really our eye will be on the NSF. This is the Industry University Collaboration Program at NSF. They support centers, which is very relevant to our work. And they have 2 calls, one in January and one in December for these centers. And again, we'll have the organizing of our data centers and maybe small molecular just to show a proof of concept that quantum machine learning and quantum computing can be combined to do these calculations. And in the second year, we can look for other funding like DOE. They have a lot of interest in this field of quantum computing for the material design and other projects. And we'll have symposium review. And then we have with the classical data, there is a classical machine learning. And the question, we can compare our quantum machine learning with the classical machine learning for a small database. And thank you for your attention.
Sabri, so help me out here, okay? So we don't have any practical quantum computers yet. I mean, D-Wave, but that's a special.
Yeah.
Right. So how are you gonna combine quantum computing?
Yeah.
You're gonna develop algorithms for machine learning that would be suitable to a quantum computer.
Sure. Yeah.
Right. As you could develop an algorithm for Monte Carlo on a quantum machine, right?
Sure, yeah. Mm-hmm.
But how are you going to prove it? How are you going to test it?
Yeah, I think
in the absence of a quantum computer.
Yeah, I think it's not. I mean, still IBM. They released for the public 5 qubits. They have 16 qubits. We have access to those 16 qubits. Yeah, we have access. We have collaboration with a group doing quantum computing there with Jack Gambita. And then the 21, you have to pay for that. But we have collaboration with the Oak Ridge National Lab. Oak Ridge National Lab bought the 21 qubits. So we can do our test with the 21.
Test your algorithms on IBM's quantum machine.
Yeah, at least that if we need 21, we'll go to the Oak Ridge because we have collaboration and they said we can have access to the 21. Unless Purdue will give us the funding to.
There you go. We'll talk to Microsoft about it. Okay. No, okay. I didn't realize that. That's interesting.
Yeah, they have 21 operational qubits with IBM.
What do you estimate? I mean, if you're actually able to develop machine learning algorithms
Yeah.
on quantum computers.
Yeah.
I mean, you talk a little bit about amount of data and so on. What do you expect the biggest impact to be?
I think we started because our expertise in quantum chemistry, so we are the first group to combine electronic structure, because we have quantum algorithm for electronic structure, and we succeed to combine it with machine learning. And the machine learning in this case is the Boltzmann machine. So we combine both together, and we show that one can do quantum machine learning for the first time for electronic structure. And we did the water system. Water is like it's a small system, but still we proved the concept that one can do it. And we are happy we can submit it to Nature, and this with the referees now. So this was last month.
So again, so my question comes from a complete lack of knowledge
That's
about
fine.
quantum computing, so please excuse the naivety. But so I know that using quantum computers so far, the most successful application has been in the atomic scale simulations, right?
And
When they
molecular simulation too.
atomic simulation,
For quantum computers?
yeah,
Not also molecules, because IBM released molecular system, yeah.
molecular level, yes.
Yeah,
But there's a lot of stochasticity and so on, so it makes sense. But when you're talking about something like the electric grid,
Yeah.
help me understand
Yeah.
how, 50 qubit computer, what scale of simulation or of
Yeah.
learning, and
Yeah.
what type of learning are we talking about here?
Yeah, for that one, in the machine learning, I mean, Alex is here, but what we build there is the covariant matrix. I mean, you have a vector of information, you multiply by the transport, and you have the covariant matrix. So what you do in classical computation, you diagonalize it to get the principal eigenvector for this one. In a quantum computing, we have speed up. We have speed up for I have this slide. We go from D to log D in finding the eigenvalues. So I think in a quantum computer also we can analyze these covariant matrices.
So it's in these very specific tasks. That
Yeah, so I think if you do linear algebra like matrix manipulation, inverting a matrix, multiplying vectors, analyzing data, you have a speed up in a quantum versus the classical. But I thought with the approach, we can just, for a small database, we can prove the concept that one can invert a matrix, one can manipulate finding the diagonal, the largest eigenvalues of a covariant matrix. So covariant matrix in a quantum mechanics means the density matrix.
So in that regard, what is the state of the art, and where's the competition?
So the state of the art is actually, so we've got about 1,000 PMUs, as a phase measurement units on the electrical grid currently in the US. This number is supposed to go up because there's an initiative to put more and more sensors to look at the oscillation monitoring of the system. So actually in a paper that I wrote with a couple of people from Washington State in the electrical engineering, the power grid modeling group, that's a very strong group. So we've shown that you can actually model about 1,000, 1,500 sensors, and you can do it faster than real time using a classical algorithm.
Right, so I guess my question
Yeah.
was in terms of the quantum machine learning algorithms for
Yeah.
principal component analysis.
Yeah.
What is the state of the art?
So there you actually have, theoretically, you have exponential speed up. So he had a slide, actually, maybe you can
Yeah.
go back to the slide. You have exponential speed up there. So the question is that practically realizable? That's probably,
But it's like nobody has done it. This is all new. So okay. So it wasn't done yet. So no. I don't know. There's no information about like how the quantum machine works for this one. But we know like in principle how this is going to work. But we have no results. Nobody did it.
So no one else has.
No one else did it. No.
yeah, the people have designed algorithms, so people publish papers, but they haven't published results.
And just very quick question about your security point.
Yeah.
You're really talking about insecurity there, right?
Breaking the code. Yeah.
factorizing.
I mean, how do you factor large numbers with a quantum machine? Yes.
So
Yeah.
it's exposing the dangers of being able to break crypto rather than solving that. Am I right? Or
Yeah. So I think both are important. Break it.
We'll get there first. Do we or does somebody else?
So on the next slide, you sort of motivate this with 4 applications, and I'm curious, can you say something about how you anticipate your team working together around this? Is this application driven, or how do you see this going forward?
We are focusing on both. First, the algorithm, because it's still a new field. Nobody combined both. I mean, I mentioned like a few groups are working, but there is no real results. Nobody really showed that. We just submitted the paper for electronic structure, which is the first project for the machine learning. So it's an early, nobody knows exactly how this is going to work, but the promise is that we have a speed up. And the speed up, we're going to use it for this because there is a classical machine learning for the 3 algorithms. People already use classical machine learning for data, for material design. And I say with the classical machine learning for also for the grid stability and for solar. Professor
What was the electronic structure? Was it density functional theory?
Yeah, this is the functional theory, and I think the project was at Harvard with MIT. This is the Green Energy Project, and they were able to put 3 million compounds with DFT. So we have a database with the 3 million DFT calculations for electronic structure. And they use machine learning to really narrow it down to 100 candidates, and the experimentalists choose 20 out of them to do a real experiment.
And I want to add that DOE has been supporting quantum computing for
Yeah,
some
DOE.
time, and in fact, in the next couple of years, they're going to put in large centers. So this is actually, this is not pie in the sky anymore. People are actually putting money in there. Industry is working as well.
Sabri, thank you very much.